Okay, let's start. Hello, everyone. Welcome to our second session of this Connection Wednesday webinar. Good evening to all of you joining from Europe. Good afternoon to those who are joining from the other side of the Atlantic. This second session is, we usually have a mixed audience from all different continents, so it's quite interesting. So thank you all for taking the time to follow this session. My name is Theodore. I'm a director at StatiCa UK, and together with Kostis, our support manager at StatiCa UK, who is going to do most of the presentation, we have prepared some nice things to show you. I hope that you will find interesting. Before we start the presentation, I just wanted to mention a couple of things for those who hasn't used GoToWebinar before. So in the right side of your screen, you will see a control panel, and this is where you will see a question tab. This is a place that you can put any question that you have during the webinar. You will be muted by default, so if you have anything to ask, just add this question to the questions tab and we will answer them during the webinar, and hopefully we will have some time also at the end for a quick Q&A. I will quickly go through today's agenda. So in the first part, we are presenting a customer project, which is coming from Wentworth House Partnership, and it's a connection from a shaft tower from Thames Tideway Tunnel project. I will discuss a little bit about that in a few seconds. So the second part is about the HelpDesk example. And so that means a support request that we've had from one of our customers, and we think that it is interesting to share with you. So today we have an example where we will show you how you can reinforce the web of a wide column with doubler plates without affecting the length of the column. In the last part, if we have some time and if there are any questions, we will have a quick Q&A session. Before we start, I think it would be interesting for all of us to see how many of you are using StatiCa already and what is your experience. So I'm just going to run a quick poll. So please enter your answers. So I'm just going to run the poll and just use your mouse to click the relevant answer. So if you have used before StatiCa, what is your experience? Just go through the different options and let us know so that we have an idea of what is your experience with the software. So I see that questions are, the answers are coming in already. Very good. Thank you. Nice. I see that most of you have been using the software, but you're not very experienced with it. So I'm just going to let a few seconds for all of the participants to vote. Even if you're not familiar, just pick the relevant answer to let us know. Good. All right. I think we have almost all of the answers. So let me close this and show you the results. So I can see that most of you have half of you actually have a small experience with the software. So good. All right. So let's move on. And we begin with the customer project, which is as a connection from a shaft tower for Thames Tideway Tunnel. To give you a little bit of background about the project, Thames Tunnel is the biggest infrastructure project ever undertaken by the UK water industry. It's a massive project and has been designed to fix the problem of millions of tons of raw sewage spills going untreated into the River Thames every year. So this 25-kilometer tunnel will run under Thames River, starting from west of London towards the east and through the heart of London at depths between 30 and 60 meters, and will intercept, store, and ultimately transfer the sewage waste away from the river. So it's really a big project that will change significantly the life of all Londoners. And to achieve this, there are 24 construction sites right now in London, and more than a dozen shafts, like deep vertical holes. Some of these have been excavated to a depth for more than 60 meters. So quite big and demanding project. Now, the customer that has been involved in this project is Wentworth House Partnership. It's a leading design consultancy in the UK in temporary and permanent works, but also geotechnical engineering. Wentworth has been using Idea Statica for over 2 years now. And in this project, Idea Statica was used within the framework of a Category 3 check of a shaft service tower for one of these project locations, one of these shafts that I mentioned earlier. So today we're going to present a specific connection from this project. We're going to show you the complete workflow of modeling and checking of this joint. This is a joint between a tower, column, and 3 beams at the typical bracing level. And as you can see from the picture, the beam to column joints are simple bolted connection using fin plates. So without further delay, I will switch my screen to Kostis, who is going to show you this example.
Okay, so hello everyone from my side. Welcome to this Connection Wednesdays. And before moving to the modeling part of this webinar, let's see the distinct features of this connection. Like Theodore mentioned before, these beams are connected using fin plate, which is a really simple connection. But at the same time, these beams have these gussets here, which are welded at the top, at their top, and at the same time, they're welded at the column. Moreover, beams B3 apostrophe and B3 quote stand on this horizontal gusset, which is also used for the bolting of this diagonal here. Okay, so let's move on and try to model this from scratch. I will create a new connection and start the model from scratch. And the first thing is to add a new member, which will be the column. I will rename it to C1. I will go with the hollow cross section, rotate this cross section by 90 degrees, and set its type to continuous. Next, I will add my first beam. The beam will be named B3. Its cross-section will be a UB 254, which is already defined. I will move it at the horizontally, and then I will change its geometrical type to ended. Then I will set its direction. Let's use this cube here to rotate it slightly. And then, since I will use a copy operation, at this point I will set its forces property to be in the bolts. This means that the shear forces I will define later on will pass through the bolt columns of the fin plate. Again, I will copy this operation, rename it to B3 apostrophe, and move it to -90 degrees. Again, copy, rename the beam to B3 quote. I'm using the names of the original cross-section, and set its direction so that it is coming diagonally. Next, I will start positioning my diagonals. I will create a new member. This will be the horizontal diagonal. For this, I will use an angle cross-section. I will change its direction. Use the mirror option. And now I will use these offsets to move it in place. Generally, we don't recommend using these eccentricities for member positioning, but in this particular case, this is okay, as I will change the model type to an VY-VZ, which means that only axial and shear forces are allowed, and this option prevents the development of moments. Now I will use these eccentricities, which will not create additional moments. And I have this diagonal in place. I will then copy it. Change its direction. Slightly incline it. Rotate it along its axis. And then add some eccentricities. I will remove the mirror Y option. Again, I will copy it, rename, I will rotate it so that its rotation matches that of the diagonal beam, change the inclinations, and my diagonal is in place. So there it is. I have positioned my members, and I will move on, and I will connect them. Before moving to the connection of these members, let's have a look at the original cross section. And please notice that all members are cut at a distance of 50 mils from the hollow section. Also, please notice that this member is cut in order to allow the diagonal beam to be positioned in place. In order to realize this cut, I will use an operation that was recently introduced in IDEA StatiCa, and which is called the negative volume. Now, using this operation, I'm creating a volume from a member, and I'm using the outer surface of this fictional member to cut all my beams. Since they have a constant distance from the outer surface of my hollow section, I will create a new fictional cross section using the cold formed definition. Please note at this point that since this is a fictional volume, it doesn't matter if it's welded, if it's cold formed, etc. We're only using its shape. So I'm defining a 300 by 300 hollow cross section. I don't care about the thickness and the radius. I will rotate it by 90 degrees and increase the lengths. I will then have a look from the top, and I can see that I can use its surface to cut my beams. Please notice that here we have the beam that falls straight on the rounding of this cross section. So I will move back to the definition and slightly increase its dimensions. And at the same time, I will add an offset, which will maintain a constant distance from all beams. And next, I will use the cut operations and start cutting the beams one by one. So I will start first with this beam, which is B3 quote, and I will cut it using the negative volume. If I look from the top, you can see the result here. Again, I will copy, change beam to B3, again copy, and change beam to be cut to B3 apostrophe. And the cuts are in place. Then I will use a new cut operation, and I will cut beam B3 using beam B3 quote and specifically its surface. You can see that the beam was modified, and I will add an offset of 10 mils so that I can have a distance, this distance. Now let's move on and start to model fin plates. I will use the fin plate manufacturing operation, and I will start by connecting beam B3 apostrophe. Let's look from the side and switch the view to transparent so that I can see the dimensions. The fin plate connects the web of beam B3 apostrophe to the column. Its thickness is 10 mils. I will set its overlap to 75 mils so that I can have an overall length of 85. And then I will modify the height of the fin plate as a distance from the top flange and the bottom flange. I will use M16 8.8 bolts, but now I have a limitation. The limitation here is that if I define bolts in here, the bolts are symmetrically positioned in the overlap, and the overlap is this distance of 75 mils. So I will right click and use the editor to fine tune the position of my bolts. I will switch to the drawing view. I can see that I have a distance of 38 mils from the edge. I need to have 30 mils, so I will explode the bolts and here add 8 mils so that the bolts are moved to the edge. I'm happy with the 30 mils distance here, so I'm accepting this definition by pressing the apply button and applying this on the fin plate. Let's also use solid view. Last, I will define the throat thickness of my weld to 4.2. And I can move by defining a fin plate to beam B3 quote. I will do so by copying the fin plate operation, changing the member to B3 quote. I can see here that the fin plate is realized. I will also change its location. And one thing we have to notice is that the definition of the fin plate also modified the shape of my beam. To fix this, I will use some negative definitions. So I'm using a negative gap, an overlap of 95 mils. You can see the overlap here. I can fully control the length of my fin plate. But again, I have to manually check the position of my bolts. I'm going to the editor. Since I don't want them to be symmetrically positioned, I want them to have a distance of 30 mils from the edge. I'm moving here and giving this additional 10 mils so that they move to the edge. Let me move the window and apply the operation, and you can see that the bolts moved to the edge of the fin plate. Last, I will add the fin plate to beam B3, which is an exact copy of plate FP1. So I'm selecting FP1, right-clicking, copy, and on the new definition of the fin plate, I'm adding beam B3. Again, I'm changing the location from front to rear. And the next step is to connect this diagonal here using a gusset. I will create the gusset using our gusset operation. I will relate the operation to this diagonal. I'm selecting diagonal. And the new gusset will be related to beam B3 apostrophe and also a member which is the column. I'm switching the view to transparent. And now I will modify the dimensions of the gusset. So I'm giving a thickness of 10 mils, a width of 170, and a depth of 100 mils. Then I will fine tune the type of connection. So I'm giving a gap of 5 mils. I'm aligning my angle at the front and changing its connection type to bolted. So now I will move my bolt by 24 mils and 30 mils from the edge. I can check the position of my bolt again by using the editor. I right-clicked on the gusset, and from the drawing I can see the distances from the gusset, which are 45 and 40 mils. Next, I will copy this gusset on member B3 quote. I will relate it to the relevant diagonal. And I will fine-tune the size of this gusset by modifying the width property and the depth properties. I have to fine-tune 12 also, and this is valid also for the previous gusset. And the next step is to add a horizontal gusset on which beams B3 and B3 apostrophe will be standing on, and also I will connect the horizontal angle. So I will use stiffening plate operation. I will rename it something like horizontal gusset. I will set the dimensions of the plate, switch my view to transparent, and then move it in place. Now I will use a cut of plate operation, and this will cut and weld the plate on the column. So I'm selecting my horizontal plate, which will be cut from the column using the surface cutting method and a double fillet 4.2 mils throat thickness. Now I have to connect my diagonal, and I will use the bolt grid operation. The bolt grid will be connecting two items. The first item is this leg of the angle, and the software discovered automatically the horizontal gusset. I will then modify the position of my bolt. And the last part is that I will weld the bottom flanges on this horizontal gusset. I will use a weld operation. And I will weld my horizontal gusset on this member here. I will switch my view to transparent because I want to be able to see the indices of the edges of the gusset. Some welding edge 6 and 7. I can see that the weld was created. Switch my view back to solid and then set throat thickness. And I will rotate my view and do the same by copying the weld operation for the bottom flange of beam B3 quote. Again, switch the view to transparent to find out the indices, and this time it's 8 and 9. And my model is ready to be loaded. I will create a new load case and add some effect. First, I will load member B3. And then I will load the diagonals with only axial forces. Please notice that in the diagonals where we declared that they will not accept moments, the software does not allow to input any moments, and the relevant cells are deactivated. Since it takes some time to solve this, I will move back to the solved model, and after the solution, okay, and after the solution is over, the software displays the overall check or the traffic light check, where we can see that each part of the connection is colored with a color that signifies its state. So gray part means that they are underutilized, and for plates it means that they remain in the elastic region. For green parts it means that they are utilized over 60%. There are also some orange parts, which means that they are utilized over 95% but below 100. And in some cases we have red parts that signify failure. In this case, of course, we don't have any red part. At the top left we can see a summary of the checks, and here we have some tabs that display some tables with summary of the results. We can see here that loads were applied to 100%. We can also see some non-conformity. And what is this non-conformity? Again, since we asked the software to prevent the development of moments on the diagonals, the solver provides some information about the magnitude of the moments that would be developed if we would allow the development of moments. Since the magnitude of these moments is quite small, it means that we did the correct thing. Now the next check is the local deformation check, and this check is relevant to hollow cross sections. We can see that the member passes the check. Then we have checks for plates. Now, if we want to have a better look and a better understanding of the behavior of the connection, we need to activate the strain check. this strain check displays the distribution of the check on the member. So for example, in this web here was green because of this region, but now we can see which regions are actually green. We can see the distribution. I can click on any part of the connection. For example, this flange here. I can verify my selection from this thick orange outline here. In the table of results, when I click on any part of my connection, the relevant row is highlighted in this table, and I can see the thickness of the part, the von Mises stress, and the plastic strain, which is actually the heart of our method. Then we have the bolts. Again, I have a table of all bolt results in my project. I can activate the bolt forces. And in the 3D window, I can see the tensile forces in my bolts. In the table of results, I have a list of every bolt in the table. So I can click on a bolt. At the bottom window, I can see an elevation of the plate that these bolts are bolting. And of course, I can see the position of this plate on the model. You can see here the orange outline. I can see the maximum tensile force and the maximum shear force in the selected bolt. This is bolt B4, and it's this black one here. I can see the plate bearing resistance and the other resistances here for each bolt. And of course, I can see the utilization in tension, in shear, and of course, the interaction of this utilization. Last, we have a detailing check that checks the distances of these bolts. And of course, if I click on this plus button here, I can see the checks using the formulas in the code. Enough with the bolts, let's move to the welds. In a similar manner, I have the weld results in a tabular format. When I select a table row, I can see the position of the weld in the model, and at the bottom, I can see the stress distribution of the weld. Again, if I press the plus button, I can see the code formulas and the checks. So I see that time passes by. So I will move the presenter to Theodore.
Okay.
For
Thank you, Kostis. That was great. We'll switch over to my screen. Okay, so before we move to the next part, you've seen that Kostis has used a negative volume, the negative volume operation. So it would be really interesting for us to know if you were aware of this operation. So I'm just going to quickly run a poll. So just use your mouse to select either of these options. Negative volume is an operation that was added in version 10, so it's relatively new, so it would be interesting for us to see if you were actually aware of this and if you have used it so far. I see that, yeah, lots of votes are coming in. Thank you. That is great. I'm just going to let it a few seconds more. That is okay. Very well. Very well. I see that most of the participants have answered already. So I'm just going to close the poll and share the results with you. So 62% were not aware of this operation. So that's good for us that we actually chose to show you this. This is a really nice feature that can help you a lot with the modeling. So make sure you, if any of you have a license already, make sure that you try it out a little bit and see where it can help you. All right, so let's move on. So Kostis, I'm going to switch over to you again, and let's move to the next part, which is the help desk example.
Okay, so in this example, I will demonstrate the problem that our client had. He's using a really slender column here, and he was trying to analyze it. And if we move at the check, at the strain check, we can see that the original configuration with the stiffeners was failing. So our client decided to add some doubler plates and see how the column behaves. Again, let me activate the strain check. And with the addition of the doublers, you can see that at the position of the doublers, everything is okay, but the failure is concentrated at the bottom. So our client decided that he would further extend doubler plates. But the problem here is that when we extend the doubler plates, the software is also extending the member to enforce a rule we have, which is essential for our method, and extends the member by 1.5 times the member height to enforce a smooth stress flow during the isolation of the connection. But when members become too long, there are problems because we move away from the node, and in this, again, in this using this option, you can see that the failure moves at the bottom. So we need to find a workaround for this case. So we'll use the original. I will use the original configuration. Go to the design, and I will remove the stiffeners. Since the problem is the problem we have to fix is that we need to prevent the column from becoming too long. Okay. But how can we do this? Since when we add doubler plates, the member becomes longer. And the answer is that we need to create a new cross section with the doubler plate included. I will move to the materials, and here I will create a new cross section, and I will create the general cross section feature we have. Here I'm creating the general cross section from part. So first I will use the UB, the original UB cross section. It is an 838 by 292 mils cross section. And now I will add a new part, which is a general plate. This general plate is 15 mils thick and 750 mils high. I will insert this here, rotate it, and now I will relate it to my UB section so that I can use these numbers here to position it. So I'm relating the plate. The plate is related to this point here, so I'm adding some offsets. And you can see that now it's in place. I will copy my plate, set the appropriate point and the appropriate offset, and the second plate is in place. I'm pressing OK. I will change the name to custom cross-section, move back to the design, select my column, and I'm applying the custom cross-section I just created. And you can see here that the doublers are part of the cross-section, and my column does not grow. Now let's try to activate the stiffeners. The next problem, the next challenge is that my custom cross-section cannot have stiffeners using the stiffener operation. But I will create a new general stiffening plate. Change my view to transparent. Now I will relate it to my custom member, which is member C, second bottom flange. I will set its dimensions. And as you can see from the top, it's big. This is quite big, and it moves inside the flanges. You will see why right now. I'm deactivating the weld. And then I will use a cut-off plate operation. And I'm cutting the new plate by using the surface of my column. And there it is. I have my stiffener. Now I will position my stiffener in place by using the position property. And I can also slightly add a slight inclination. And again, copy this. Set it to 350, 0 inclination, copy the cutoff plate, etc. Let me move to the original, to the fixed. Connection, so I'm calculating it. And you can see after the calculation is over that it passes all checks. Two things I would like to clarify here. The fact that I have used a cross section with doubler plates does not mean that you need to have doubler plates at the whole column length. This is wrong. We need to have doubler plates only at the region of the joint. And if you want the exact geometry, you can go here at the bill of, let's stop this. You can go with the bill of materials. Anyway, you can take the exact dimensions from this report. And the second thing is that we cannot calculate, using this approximation, we cannot calculate the welds of the doubler plates, and it is assumed that they are full penetration butt welds. So that was it. So Theodore, I think that we can move to the Q&A session.
Yep. Yeah, thank you, Kostis. All of the answers have been answered actually through the chat. And the last one that hasn't been answered, you just answered it. So it was a question: what will be the weld between the doubler plate and the column? So you just answered it. With this approach, we cannot calculate the weld. It is assumed to be a full weld. This is the only limitation, let's say, but still it's a nice approach, let's say. Let me see if there is anything else. How far below the lower stiffener does the doubler extend?
Okay, let me go in the code setup here. Here we have two settings: that the default length of member and hollow section is this factor times the cross-section height. Now this cross-section is custom. Its height is 835 mils. So it's 1.5 times the 835 mils. We can calculate this. It's this value here in mils.
Okay.
Below the stiffener, which is the last feature introduced in the model.
All right. Thanks. I don't see any other question, and we're actually running out of time. Just quickly, yeah, on the previous question, is the 1.5 times a code requirement? Are the stresses calculated?
Well, in our approach, we calculate the von Mises stress, but in the CBFEM methodology, we check the plastic strains of the member, the principal plastic strains, and this is completely in line with Eurocode 1993-15 Annex C. For more information on this, you can have a look in our resource center and specifically in our theoretical backgrounds where we explain the methodology in detail.
Yeah, I think that this question actually came from Australia, so probably you can go to the relevant part of the Australian code, right?
Yes. Yes.
Okay. Let me see if there is any other question. Okay, I don't see anything else. So I'm just going to quickly switch to my screen. Okay, so before we close this webinar, I would like to say special thanks to Ioannis Bousvoukis and Vassilios Papastathis from Wentworth House Partnership, who provided us with the connection that we showed you today and all the information about this amazing project that they participated. So thank you very much. And after the webinar, you will receive a short survey. So please take a minute to answer the questions that we have put there. They help us to improve the webinars, and it provides us with some let's say ideas of what to do in the upcoming webinars. The recording of this webinar will be available in our website and on YouTube. So until tomorrow, probably. And for those who haven't used Idea Statica before, you can download the trial version at our website, and it's a 14-day trial, so it will allow you to see the amazing potential of this software. So let's close this Connection Wednesday. So thank you very much for attending. Thank you very much for taking the time to follow another Connection Wednesday webinar, and we are looking forward to see you in the next ones. Thanks a lot. Bye-bye.
Bye.